We're looking at more trig identities today. So from chapter 4, we saw these four trig identities, the reciprocal, quotient, and Pythagorean identities. Pull out those notes. You're going to need them today. We have more, so different ways to write the same thing, basically. We have cofunction identities, which are like the cosine of u is the same as the sine of pi over 2 minus u. So this would be the negative here would be like a horizontal reflection and then shifted over pi over 2 units, and then you get the same cosine graph. So all of these are equal to each other. Write them down. All right, we have even and odd identities. So sine is an odd function, and so is tangent. These are both odd functions. So that means, like with sine, goes like this. So at u and negative u, they have the same outputs. So it's sine, but they are negative from each other. Okay, cosecant is reciprocal, so it would be negative cosecant of u is equal to cosecant of negative u. Tangent of negative u is equal to negative tangent of u. And negative cotangent of u is equal to cotangent of negative u. Cosine is the only one that's even, and it's reciprocal secant. So cosine of u is equal on the left side to cosine of positive u. And secant of negative u is equal to secant of positive u. All right, so we're going to use some of our trig identities from the past to help us solve for these ratios. So this is just another way to solve for ratios. So ratios of the sides. So first we're going to use our reciprocal identity to find cosine of u. I am, number one, going to look at where this angle is. So all students take calc, and secant is the reciprocal of cosine. So where is cosine negative? In quadrants 2 and 3. And then tangent of u is positive, so that would be quadrants 1 and 2. So my ratio is going to be in the third quadrant, okay, or my triangle. So we're going to use the reciprocal identity to find the cosine of u. The reciprocal to cosine would be 1 over secant of u. And we know that secant of u is negative 3 over 2, multiplied by the reciprocal. 2 over 3. To give us, that cancels, we get negative 2 over 3. Next up is the Pythagorean identities to find sine. Well, let's write cosine of u equals. So I know that I'm trying to find sine, so I'm going to do sine squared u plus cosine squared u is equal to 1. We'll start with that identity. And then we're going to solve for sine squared u. So sine squared u plus, cosine is this negative 2 over 3 squared is equal to 1. Simplify. Sine squared u is equal to 1 minus 4 over 9. I just moved it to the other side. And then 9 over 9. So sine squared u is equal to 5 over 9. Go ahead and take the square root. And I get the sine of u is equal to plus or minus the square root of 5 over 3, since I'm unsquaring the sine squared. And is sine in the third quadrant positive or negative? Well, it is negative, so it's just going to be negative 5 root 5 over 3. So that's our sine ratio using our identities to solve instead of just like a regular triangle. Okay, finally, a review of the quotient identity. Tan u can be rewritten as, that's right, sine u over cosine u. And luckily, I figured that out on parts AA. Sorry. So here we go. Negative square root 5 over 3. And then from the original A, negative 2 over 3, multiplied by the reciprocal. Let's do negative. Cancels. So 3 over negative 2. A negative times a negative is going to give me a positive, so I get the square root of 3 over 2. Okay? All right, so that is our tangent of u. So that's just another way to solve for our trig ratios. All right, we are next going to see some different things we can do with manipulating trig ratios. So really, all we're doing here is simplifying. Sine x is basically the GCF. So we're going to multiply this in by distributing. So we're going to distribute. Okay, so I get the sine of x times the cosecant of x minus sine x, oops, I did that wrong, times sine x times sine of x, which is basically, now I'm going to use the reciprocal property to reevaluate sine or cosecant of x as 1 over sine of x. And then sine times sine would be sine squared x. So sine over 1 times sine x over 1 times 1 over sine x, those cancel to give me a 1. So I get 1 minus sine squared x. And then I'm going to use my Pythagorean identities to rewrite 1 minus sine squared x as cosine squared x. And that is a lot nicer than the original. All right. Another thing we can do when we have identities is we can factor them. So just like normal trig identities, or just like normal factoring equations, like this kind of looks like, I'm going to rewrite this, sine to the fourth x minus 2 sine squared x plus 1. That looks like a big X problem to me. But I'm going to let sine squared x, like this middle term right here, equal u. And I'm going to substitute it in. So instead of sine to the fourth x, that would be u squared minus 2 times u plus 1. Oh, look, big X problem. 1 on the top, negative 2 on the bottom. Negative 1 times negative 1 multiplies to give me 1 and adds to give me negative 2. So I get u minus 1 times u minus 1. And then we replace u equals sine squared x back in. So sine squared x minus 1 times sine squared x minus 1. Do you have to do it like this? No, but it can help you factor that. Okay, this is basically the sine squared x minus 1 squared. It's a perfect square. All right, we're going to verify that one side is equal to the other. Remember, we start with the more complicated side. So I am going to start with the left, and I'm not going to touch the right at all. All right, so we're going to, you can area model this, or you can multiply them, double distribute here. Okay, so I get secant theta times cosecant of theta. And then I did secant theta times 1 minus tangent theta times cosecant theta. And then tangent times 1 minus tangent theta is equal to cotangent theta. And this is not that helpful for me because I have too many trig ratios here to work with. So we want to kind of get the same type of trig ratios. So I'm going to use the what's it called? Reciprocal and quotient properties to change these, to change the trig identities into terms of sine and cosine. Okay, so how can I rewrite secant theta? I can rewrite that as 1 over cosecant theta. Cosecant theta is 1 over sine theta plus 1 over, 1 over cosine theta minus, I want to write tangent in terms, I could write it as 1 over cotangent, but I want to write this in terms of sine and cosine, so I'm going to use the quotient property to write sine theta over cosine theta. times 1 over sine theta minus sine theta over cosine theta is equal to the cotangent of theta. Next, we need a common denominator of, looks like cosine theta times sine theta. So this first terms are good. We need to multiply this fraction by sine theta on the top and sine theta on the bottom. That one is good. And the fourth one also needs to multiply by sine theta over sine theta. And we're not going to touch anything on the right-hand side. All right, so I get 1 over cosine theta sine theta plus sine theta over cosine theta minus sine theta, times sine theta, and then we're going to minus sine theta over cosine theta times sine theta, and then minus sine theta times sine theta, giving me sine squared theta over cosine theta sine theta. And this is all going to equal cotangent theta. Move it over for us. Okay. All right. Ooh, look, sine theta over cosine theta sine theta minus sine theta over cosine theta sine theta is 0. Okay, so I end with, and now I have a common denominator, so I can just combine the numerators. 1 minus sine squared theta all over cosine theta sine theta is equal to cotangent theta. We're almost there. Now I'm going to use Pythagorean identities to evaluate 1 minus sine squared theta as cosine squared theta over cosine theta sine theta is equal to cotangent theta. We're even closer. Okay, I'm going to split this cosine squared theta apart as cosine theta times cosine theta over cosine theta sine theta is equal to cotangent theta. Those cancel, and I can see that the quotient property of cosine theta over sine theta is cotangent theta. So the left side equals the right side. Proved. Check. All right, next up. It says, perform the indicated operations and use identities to simplify. So I want to add these fractions. How do we add fractions? We need a common denominator. So our common denominator would be 1 plus sine x times cosine x. So I need to multiply this fraction by 1 plus sine x in the numerator and in the denominator. The first fraction, we are missing a cosine x in the denominator. So let's go ahead and multiply that. So I get the cosine squared x over cosine of x times 1 plus sine of x plus, we're going to 1 plus 1 is 1, sine x plus sine x is 2 sine x, and then sine squared x, all over cosine x times 1 plus the sine of x. All right. Oops, I forgot a plus right there. I'm going to add my numerators. So I get 1 plus 2 times the sine of x plus sine squared x plus cosine squared x. I shall use, I forgot my denominator. The cosine of 1 plus sine of x. Remember, we can use the Pythagorean identities here, and sine squared x plus cosine squared x is equal to 1. So I get 2 plus 2 sine of x over, so I'm going to cross that out and put 1, cosine x times 1 plus the sine of x. I'm almost there. GCF, the numerator, 2 times 1 plus the sine of x over cosine of x times 1 plus sine of x. Those cancel, giving me 2 over the cosine of x, or 2 times the secant of x. And we be done for today.